Thank you, Dr. Parks, for that kind introduction. I have known many of you a long time, and the great part about seminar is the discussion that we get to have afterwards. I'm so excited to share with you today some of the work that I've been doing the last couple years. To begin, I will give a brief overview of stable isotopes and lipid metabolism, and then I will introduce the concept of spillover and its role as an individual characteristic. I'll finish with a discussion of acyl carnitine metabolism. So what are isotopes? Isotopes are variants of an element that have the same number of protons, but a different number of neutrons. So here on the right, we have the atomic structure of carbon. And in the nucleus, you can see the protons in blue, the neutrons in red, and the electrons in the orange in the outer rings. The atomic mass of carbon is 12, and we refer to this as unlabeled. This is the smallest isotopic mass for the element. In the heavier stable isotope, carbon-13, there's one additional neutron, which increases the atomic mass and physical properties of the element. Isotopes occur naturally in the atmosphere, and for carbon, about 99% is carbon-12, with 1% existing as carbon-13. These elements are incorporated into a molecule of interest, such as a fatty acid. So we can give these molecules to people, and the body cannot tell the difference between the unlabeled and heavier molecules. We can buy the heavier molecule, and for our studies, we feed triglycerides with the heavier isotope incorporated into a meal to trace dietary fats. So on the left, we have a meal that Jen made for us, and we fed to participants. It consisted of a salad, green beans, a dinner roll, and chicken Alfredo pasta. The isotope is incorporated into the Alfredo sauce. On the right is a chocolate shake that had an isotope blended into it. Dr. Parks's mentor, Mark Hellerstein, said that nature doesn't leave a footprint. And what this means is that molecules or lipids can move through the body without our ability to trace or track their movement. But by feeding isotopes, we are able to introduce a heavier molecule that we can use to trace dietary fat. After feeding these meals, we draw blood throughout the night to measure the nocturnal use of dietary fats. Today, I'm going to be talking about the sources the sources of plasma-free fatty acids, or FFA. This includes adipose fat and fat from the meal. Very briefly, to review physiology, adipose tissue lipolysis releases free fatty acids that can be taken up into muscle to be stored in lipid droplets or oxidized in the mitochondria. Now, many of you have heard me talk about spillover, but I'd like to show you what spillover is and where it comes from. So after a meal in the fed state, the fat that we've just consumed is packaged and transported on chylomicrons. Here, the asterisks represent the labeled fatty acids from the meal isotope. Chylomicrons and VLDL interact with lipoprotein lipase, or LPL, to release free fatty acids. This bucket represents spillover. Spillover is the balance between the rates of chylomicron lipolysis, or LPL-mediated lipolysis, and uptake into tissues. Spillover occurs when the rate of lipolysis exceeds the rate of uptake into peripheral tissues. So in our analogy, the flow from the water spout is the rate of the release of fatty acids from chylomicrons, and the bucket represents the rate or the capacity of uptake into peripheral tissues such as muscle. When the flow or lipolysis exceeds the rate of uptake, the water will spill over the bucket. And so in this case, it's the spillover of free fatty acids into the plasma FFA pool. Now let me show you where spillover comes from. So I talked about how chylomicron interacts with LPL to release free fatty acids. These free fatty acids can be taken up into tissues, but the ones that aren't taken up spill over and remain in the plasma FFA pool. These are those spillover fatty acids. While at the same time, adipose might still be releasing fatty acids. We take these free fatty acids out of the blood and we can run them on the mass spec to see which fatty acids are labeled and which are unlabeled. The importance of the label comes not from the concentration itself, but from the kinetics. Spillover is a result of turnover and enzymatic activity, and that's what I'm interested in. Here we have another schematic to present spillover. So on the right, we have free fatty acids from adipose tissue that are delivered to muscle, carried on albumin. On the left are chylomicrons carrying meal triglycerides. Chylomicrons interact with LPL on the endothelial membrane to release or lipolyze fatty acids. These fatty acids from either the adipose tissue or chylomicrons can be taken up into muscle to be stored in lipid droplets or oxidized. But not all of these fatty acids are taken up. And so the fatty acids that remain out in the plasma end up on albumin to stay in the FFA pool. So why do we care about spillover? Elevated concentrations of plasma-free fatty acids are among the hallmarks of metabolic disease that contribute to cardiovascular risk, insulin resistance, and ectopic lipid deposition. We are all familiar with ectopic lipid when fat is stored in organs that are not supposed to be storing fat, like liver and heart. In the fasting state, plasma FFA concentrations are supplied by many sources, but predominantly by adipose fatty acid release. However, in the fed state, spillover can be a large contributor, representing up to 40% of the total FFA concentration. We know that elevated plasma FFA are known to disrupt organ lipid homeostasis, and high levels of spillover may contribute to the negative effects of elevated plasma FFA observed in cardiometabolic disease. Oftentimes when I read about fatty liver, it is said to be due to adipose insulin resistance, but the problem with this is that many of these studies are done in the fasting state, when most of the fatty acids are coming from adipose. However, we are rarely in the fasting state, and I hypothesize that ectopic lipid can come from spillover in the fed state. So now let's get into the data. We currently have a paper in review in which we analyze data from 5 past studies from the Parks lab, 4 of which were performed by previous lab members and 1 of which I contributed significant data to. But the question that I'm currently investigating is buried in the data of all of these studies together. So the first study investigated healthy male subjects, while the remaining studies included participants who were healthy or had insulin resistance, hypertriacylglycerolemia, or metabolic dysfunction-associated steatotic liver disease. You can see that BMI and insulin varied widely. In all of these studies, participants were fed meals that contained stable isotopes, and the meal composition ranged from 30 to 45% fat, 35 to 55% carbohydrate, 10 to 20% protein, and represented 40 to 67% of total daily energy expenditure. So now to orient you. On the x-axis we have time, and FFA concentration in millimole per liters on the y-axis. In this study, participants with insulin resistance and hypertriacylglycerolemia, or high triglycerides, consumed identical meal shakes that contained the meal isotope at 6 p.m. and again at 12 p.m. the next day. In the black is the total FFA concentration, and in the light blue are fatty acids coming from adipose. And so what we can see is that after the carbohydrate-containing breakfast, FFA concentrations substantially fall, and as the insulin effect wears off, they begin to release, adipose releases again. 6 hours after dinner, represented by the green circles, we can see that dinner spillover is clearing throughout the night. And after the late breakfast, in the orange circles, breakfast FFA is spilling over into the FFA pool. So this was after an extended fast. Now let me show you what this looks like after 2 consecutive meals. Here we're looking at triglycerides from the meal and millimole per liter. These participants had 2 identical meals with different isotopes, which allows us to detect dietary fat from the meals fed 5 hours apart. In the black, you can see total TG, and you can see that the concentration increases following the meals and then decays throughout the night. In the orange, lunch TG follows a similar pattern until dinner is fed, and at about 10 p.m., dinner has left the FFA pool and spillover from dinner is, sorry, I said that backwards. The orange is lunch, which is gone by 10 p.m., and at 10 p.m., dinner is spilling over in the green. So these two meals were identical. Why do the curves look so different? We now know that this is because of the lunch TG, which is in this purple circle. So Frayn's group studied 10 participants who underwent diagnostic gastroscopy. They fasted overnight, and then they were fed breakfast that had 50 grams of fat at 7 a.m. 5 hours later, they were fed a second meal of either 38 grams of glucose or water only for controls. At 1 p.m., the procedure and a jejunum biopsy were performed. So now we can see in these electron micrographs on the top, this is a picture of the intestinal lumen, and we can see the brush border. The top picture is someone who had the glucose and water, and the bottom is just water. So there was no glucose in what they drank. What we can see is that in the participant who consumed the glucose, there are much smaller and many fewer lipid droplets compared to the person who had only water. Without consuming the glucose, breakfast is stored in the intestine, and we can see the large lipid droplets in the enterocyte, suggesting that following a high-fat meal, a portion of the fat load is stored in the intestine. Participants who consumed glucose did not have as much stored lipid, which suggests that immediately following a second meal, stored lipid is mobilized in blood to prepare for the incoming meal, and this results in a rapid increase in plasma TG. We call this the second meal effect. So now if we look back at the data, what we can see is a rapid increase in TG right after the second meal is fed. This is due to the intestinal release of stored lipid from lunch, shown in the orange. So now that I've shown you the triglyceride concentration, let's look at FFA. This is a bit complicated, so we're going to go through it step by step. In the black is total FFA, and what we can see is that it's falling and coming back. This is comprised of what's coming from dinner in the blue, lunch in the orange, adipose in the blue, lunch in the orange, and dinner in the green. Few people are aware that meal fatty acids contribute to the total FFA pool, and before adipose fatty acids are suppressed, spillover of meal fat is peaking right when we don't want them to. When adipose is contributing the most, that's also when we're getting the most fatty acids from the meal. And so this ends up almost doubling our total free fatty acid concentration. At 8 p.m., total FFA concentrations take a sharp decline due to the carbohydrate in the meal. And while adipose is going down, spillover from both lunch and dinner are filling that FFA pool back up. You can see that after meals, if you don't have the suppression of adipose, while you have spillover, you will have much higher FFA concentrations. Next, we wanted to test the effect of body composition on the spillover process. With fat mass in kilograms on the x-axis and peak spillover concentrations on the y, we have healthy subjects in the open circles, and the closed circles represent participants with metabolic disease. We found a negative and non-significant relationship between fat mass and spillover. We do think that meal is clearing to adipose tissue. It did not appear to correlate with fat mass, but it did with lean mass. In other words, lean mass plays more of an important role in dietary fat clearance and may provide protection from spillover by improving the uptake of fatty acids and reducing total plasma FFA concentrations. Katsanos and colleagues have shown that spillover increases with aging, and this may be yet another reason why exercise is important as we get older. So now that we are familiar with spillover, I would like to show you how spillover plays an important role as an individual characteristic. So I already showed you this graph. in which people with insulin resistance and high triglycerides had dinner and a late breakfast. But these lines represent the average of the entire group. And so across all people, we wanted to compare spillover 6 hours after the dinner and breakfast. Here on the x-axis is TG from dinner with breakfast, TG on the y-axis. We found that the people who had the highest amount of TG from dinner in their blood were the same people who had the highest amount of TG from breakfast in their blood. Similarly, the people with the highest dinner spillover had the highest from dinner, also had the highest spillover from breakfast. Comparing these data between subjects lets us know that spillover is an inherent characteristic of an individual, no matter when they eat a meal. We also found that subjects who had the greatest dinner TG were those who had the highest dinner spillover. We found the same relationship following breakfast. This supports the concept of spillover of FFA may be driven by the availability of the precursor or the chylomicrons carrying dietary TG. And so now that I have shown you that spillover is an individual characteristic, it made me wonder if there was anything we could do to reverse or minimize the risk associated with elevated FFA concentrations. As many of you are familiar with, we recently completed a study with Dr. Rector's lab to investigate a diet and exercise program designed to improve insulin sensitivity and lower liver fat. My goal was to use data from that study to test the effect of treatment on spillover. We collected metabolic measurements before and after the intervention, and during these study visits, participants consumed the chicken Alfredo meal that I showed you. It had a triglyceride isotope in it. So now, on the left, we have control subjects, and on the right, we have treated subjects. The open circles are baseline, and the closed circles are follow-up. We found no difference in the nocturnal presence of meal TG in controls or treated subjects. And there was no difference in our control subjects of the amount of spillover from the meal. However, our treated subjects had a 23% reduction in nocturnal spillover, and it remained significantly lower all throughout the night. This happened after 10 months of diet and exercise. So this suggests that an intervention with diet and exercise improved the subject's ability to clear dietary fats. So this brings me back to asking, is there anything that we can do to reduce or minimize the metabolic burden of spillover? In order to reduce spillover, we either need to slow the flow or the rate of LPL-mediated lipolysis, or increase the rate of uptake or the capacity, so the size of our bucket. We hypothesized that exercise increases the uptake of fatty acids into peripheral tissues, which reduces spillover. Park's lab and Rector lab have talked a lot about how exercise can lower liver fat. My data suggests that this is one way that muscle can use meal fat to lower liver fat and protect the liver. To show this effect, we have peak meal TG on the x-axis and peak spillover on the y. We found a very strong relationship in our subjects at baseline. However, this relationship was lost following 10 months of diet and exercise. We believe that the magnitude of TG drives spillover of FFA at baseline or in insulin resistance, but with 10 months of diet and exercise treatment, clearance of fatty acid to tissues increases and the concentration of TG has less of an effect on spillover. Lastly, we wanted to test whether we could use acylcarnitines to detect intracellular processing of fatty acids using a meal-stable isotope. So far I've been talking about spillover, which are the fatty acids that remain out in plasma and are not taken up into muscle. But now I'd like to pivot and we're going to talk about the fatty acids that are taken up. Plasma-free fatty acids that are targeted for beta oxidation are transported into the mitochondria using the CPT system. When fatty acids are shortened through beta oxidation, they may build up which signifies incomplete beta oxidation. The excess shortened fatty acids can then leave the mitochondria and exit the cell back into plasma. There are different acylcarnitines for all potential fatty acids coming from the diet and lipid droplets. However, long-chain fatty acids are the most common, such as 16O or palmitate. Increased acylcarnitines are thought to be indicative of insulin resistance. However, if a healthy person runs a marathon, after the race, they will have a lot of plasma acylcarnitines, which serve as a marker of entry, oxidation, and exit from the muscle. So people who run a marathon are not insulin resistant at the end of the race, but they have evidence of a lot of fatty acid movement. Let's first look at acylcarnitines without an isotopic label. So here we have lean mass in kilograms on the x-axis and postprandial acylcarnitine palmitate concentrations on the y. Acylcarnitine 16O or palmitate represents fatty acids that entered the mitochondria, did not undergo beta oxidation, and cycled back into the plasma. We found a non-significant relationship between lean mass and plasma acylcarnitine concentrations. But when we looked at acylcarnitine 10-1, which is the result of beta oxidation of oleic acid, which oleic acid is the most abundant fatty acid in human blood, in the human diet and in our blood, we found a strong relationship. And so those people who had the most lean mass had the highest acylcarnitines. Acylcarnitine 14-2 is the result of 2 rounds of beta oxidation of 18-2 linoleic acid. And so what this suggests to us is that with higher lean mass, we can expect increased acylcarnitines after a meal and in the fasted state. This supports the role of skeletal muscle in the production of acylcarnitines. But the relationship is much weaker relative to fat mass, suggesting that fat mass isn't burning as many fatty acids. I want to remind you that when we talk about spillover, I'm talking about the lack of fatty acid uptake, while the presence of acylcarnitines in plasma is the opposite of spillover. Acylcarnitines are fatty acids that were taken up, interacted with mitochondrial enzymes, and re-entered the plasma compartment. And so I'll say that again. Spillover is the result of the lack of uptake, while acylcarnitines are evidence of entry to and exit from the mitochondria. This led me to question whether spillover was inversely related to acylcarnitines. So I know this is complicated, but what I'm showing you is the relationship between spillover, those fatty acids that are not taken up, and then acylcarnitines, the fatty acids that went into the muscle and came back out. In our data, the participants that had the lowest spillover were those who had the highest acylcarnitine 16O in the blood. And the same was the case for 10-1. So these data support my hypothesis that greater muscle mass is associated with greater uptake of free fatty acids and movement into the mitochondria, regardless of whether or not they were fully oxidized or not. I'd like to come back to the schematic to just show you how the meal label cycles all the way from being consumed to being lipolyzed, taken up into muscle, into the mitochondria, and then back out into the plasma. And so now I'm going to end with a little bit of acylcarnitine data from a study that had never been done before in humans. So on the top, we have data from a male subject, and the bottom is data from a female subject. Both subjects consumed meals with dietary isotopes, 2 identical meals, that had 65% fat and provided 45% of energy needs per meal. And so we have acylcarnitine concentration on the y-axis across time. And the dark closed circles are the total acylcarnitine concentration, which is comprised of the unlabeled in the open squares, and then the acylcarnitines that are a result of the labeled fatty acids that we fed in the meal. And those are the lighter blue closed squares. So we were able to detect the label in acylcarnitines made from the meal fatty acids in 16O. In our male, it represented 23% of the total acylcarnitine meal after they consumed 2 meals, and 29% in the female. The labeled acylcarnitine 14-0 underwent 1 round of beta oxidation from the labeled meal palmitate, and it contributed 21% and 26% of the total acylcarnitine 14-0 pool. Surprisingly, even labeled acylcarnitine 12-0 was detected. And so these acylcarnitines underwent 2 rounds of beta oxidation and then left the mitochondria to go back into the blood. This proves that we are measuring beta oxidation byproducts because 14-0 and 12-0 are really low in the human body. We were even able to find the label in 10-0 and 8-0. Combined, these data provide direct evidence that plasma acylcarnitines can be produced from the oxidation of meal fat and traced non-invasively using stable isotope labeling. To summarize, I have shown you that plasma FFA concentration is not just a reflection of adipose fatty acid release, especially when people have a lot of body fat. High-fat diets can increase plasma FFA concentration through spillover, which increases the risk of ectopic lipid. Spillover of dietary fat is reproducible in a person throughout the day. And what I mean by that is that somebody who doesn't store dietary fat well from lunch also won't store dietary fat from dinner very well. Fortunately, diet and exercise can reduce dietary fatty acid spillover. The people in our MASH study showed us that diet and exercise can help with the clearance of meal fat to tissues where it's meant to be stored. And stable isotopes can be used to trace dietary fatty acid entry into and exit from the mitochondria and their oxidation non-invasively in humans. This method could be used in exercise or weight loss studies in which we are testing a hypothesis related to muscle fatty acid metabolism or oxidation. The bottom line of all of this is that we eat food that contains fat and it should be stored in our tissues. When it isn't cleared and it ends up in the plasma, it contributes to ectopic lipid in organs that should not be storing fat, like liver or heart. I'd like to thank everybody that helped make this research possible, the funding agencies and my doctoral committee, and I'm happy to answer any questions. Thank you. Yeah.
So in the context of spillover, let's say for the insulin resistant, let's say like the NEP, what do you think would have happened if we had implemented more resistance?
Oh, that's a good question. So the question is, in the study, the treatment study with diet and exercise, if we had implemented more resistance training, what would the effect be on spillover? That's a good question. I think that there probably would not have been as strong of an effect on spillover, but I think that just having the exercise was enough to see the reduction. So I don't know if what type of exercise makes a difference for spillover. Yeah. Thank you.
How long were the items given like, do they have several meals with you before they get the isotope and start tracing, or do they come in having eaten whatever they want for breakfast?
Okay, so the question is, how long are participants with us before we feed the meal isotope? If they're eating whatever they want before the meals, or kind of if it's controlled. So it depends on the study design. For the NASH study, they came in at about 4 p.m. and we fed dinner at 6, but they were provided all of their meals. So the meals that they ate before the visits were controlled. Mm-hmm. Yeah. Mm-hmm. Mm-hmm.
we were also assessing those short chain fatty acids and sugar.
Okay, let me see if I understand the question right. So the question is there a way we can use the method of like tracing acylcarnitines to track not just long chain, but also short chain fatty acids? That's a good question. Um, I would, mm, I would think not be, yes, you can label short chain fatty acids, but I would think that it would be really hard. I'm sure you could do it, but it'd be really difficult to trace short chain fatty acids because there's less like allowance of beta oxidation. So we can trace palmitate that goes in and isn't oxidized and comes back out. But if you only start with 2, 4, 6 carbons, you kind of don't have the as much wiggle room to get byproducts. Does that make sense? Yeah.
All these characteristics, they contribute to the one that behave faster.
Yeah, so does the type of fatty acid of short chain, long chain, saturated affect the way that it's cleared? Is that what you're asking? Yes. So saturated fatty acids are cleared slower or less preferentially than unsaturated fatty acids, but I don't think that the chain length has an effect on clearance. I could be wrong, but I don't think. Mhm. Thank you.
Exercise will decrease enterocyte mitochondrial content.
Hmm.
Think measure that in humans. Think that contributes to reduction in the spillover is that the enterocytes are actually utilizing the lipid. Is that something that we can target that would have meaningful impact on lowering?
Okay, so the question is, can we test the effect of improved mitochondrial function in in the enterocyte? And then can we target that to reduce spillover? Does that capture it all? Okay. Um, I would say yes, you could probably test the mitochondrial function the same way we do with liver tissue if we had tissue, like in tissue from the intestine. And then if we could target it, um, I was, yes, I think there's something that I was reading about like CYP7A1 and it kind of controls the uptake into intestine. And so I think that if you could almost the opposite of that, of increase the, well, if you increase the uptake while you're increasing the oxidation, then I would think that you would have lower spillover if it's not coming back out and not getting that chance to not be taken up. If we use it earlier in the process, I would think yes. Mhm. Yeah.
What do you think is going to happen if we try and low fat diet?
So high fat diets do increase the amount of spillover, and that comes back to the kind of our precursor product hypothesis that the more triglycerides going through, then the more spillover we're going to have. So if we had fed a lower fat diet, I would have expected lower spillover. Yeah. I mean, there's always a balance of high fat or low fat and high fat and high carb. So just a balance between all of it. But avoiding a high fat diet is beneficial for to reduce spillover. Yeah.
So I'm interested in your acyl-carnitine
Mhm.
weight mass relationship.
Hmm.
How would that change in someone who is, for example, really highly trained? And would that relationship change in aging? So as muscle quality kind of goes down, does that affect that relationship?
Okay, so the first part of the question was how would the relationship between lean mass and acylcarnitines change in someone who's highly trained?
Yeah.
And then kind of the opposite of how would that change with lower muscle quality with aging? Um, So I would expect that with somebody who's highly trained and has more muscle mass, we would have this like the same or very similar relationship where the more lean mass they have, the more acylcarnitines, even if their mitochondria are more efficient, I think we're not gonna lose the byproducts of incomplete fatty acid oxidation. And so I think the relationship would remain. And then for aging muscle, I would say that the relationship would weaken because people with the same amount of lean mass would have more incomplete fatty acid oxidation from the lower muscle quality, and so they'd have more acylcarnitines. So it'd kind of shift our.
Yeah. I guess I was just wondering if it was driven by just mitochondrial, like fat oxidation, it's just pure fat oxidation, or if it's the efficiency with which those fats
are oxidized. I think both, because you're not going to have the acylcarnitines if you don't have like I guess if you're too efficient, you're not going to have the acylcarnitines. Does that make sense?
Does spillover go up with the aging?
Spillover does go up with aging.
Why do you think that is?
The muscle quality, there's less LPL, and so you're gonna like lipolyze those fatty acids, but they're not gonna be taken up, and they'll remain. The transporters go down.
One other question I have too is what happens to the acylcarnitine?
Like in the blood? Oh, I would think that they could go into a tissue at a later time and be used.
Great job.
Thanks.
They go into urine.
Okay.
Oh, I was wrong. UP then.
That's how the body makes fatty acids not toxic. It puts a carnitine on there, which makes it water soluble. So now you're peeing out fatty acids, which is really amazing to think that, right? To get rid of fat. You can either get rid of fat by liposuction or you can eat it. Burn them up. Right.
Yeah.
You mentioned like muscle quality, but that doesn't necessarily. But there's so many components here, like the lean mass.
Right. And so that's our relationship here, that the more lean mass you have, the higher the acylcarnitines.
Thank you very much.
Thank you.
Actually, I work from.
Yeah.
Sorry.
Hi, Talia.
So for people with metabolic dysfunction, slash MASLD, slash insulin resistance, low fat diet is recommended to reduce spillover. How do you balance that with the recommendation for a low carbohydrate diet and reduce DNL? In other words, in your opinion, which dietary component, fat or carbs, is more detrimental to health within this climate?
Okay, so this is very similar to Jen's question of should we be recommending a low-fat diet and then comparing that to the recommendations for low carb. And in this case of metabolic dysfunction, MASLD, insulin resistance, kind of which is the winner. For this situation of spillover, I would say high-fat diet should be avoided more than high carb because of the effect on spillover. But we also don't want high carb because we don't want increased DNL. No, it's the sugars. Yeah. So I would say low fat diet is superior. Thanks.
Gonna get clap for it, yeah.